we thank you all for joining us on time. So to get things started, I would like to welcome our chairman, vice chairman, Mr. V.K. Raman, to welcome the gathering.
Okay, thank you, Vignesh. Am
Yes,
I
sir.
audible?
Yes, sir, you're audible, sir.
Okay. Good afternoon, fellow Foundrymen. It's my immense pleasure to welcome you all for this wonderful presentation to be made by Mr. Thirugnanam, Senior Foundry Consultant. You all know very well that any foundry has to focus the cost of production, the conversion cost, the raw material cost to achieve the EBITDA level and the reasonable P&L level. So in this connection, the main focus should be on the yield part. Where the yield is at good level, definitely there will be a reduction of conversion cost and material cost. So today, Mr. Thirugnanam, Senior Foundry Consultant, is going to present us and share us on success stories of yield improvement on die casting, prominently in gravity die casting and tilt die casting, which will enrich our knowledge to focus on those areas. So let us fully involve in this presentation, and we can ask as much as questions at the end of the session to Thirugnanam, and he will be in a position to give the answer for all the questions. So now I request Vignesh Ramanan, our Secretary, IIF Chennai Chapter, to introduce Mr. Thirugnanam to the forum and to take the presentation thereon. Thank you. Over to Vignesh.
Thank you, Raman, sir. So it is now my pleasure and privilege to introduce Mr. M.Thirugnanam, specialist in aluminum high pressure, gravity and tilting gravity die casting. He has employment experience of 35 years, consulting experience of 15 years, and training experience of 20 years. He is a BE Mechanical, having around 50 years of experience from wide spectrum of aluminum foundry industry and foundry processes. Proficient in Japanese, Chinese, German languages, understands Korean, Spanish, and Italian. He was trained in Buhlers, Switzerland, and in Suzuki Motors, Japan, in high pressure casting and GDC. Trained in Dairin Hyundai in South Korea and Bridge Foundry in England in gravity and tilting gravity die casting. He presented technical papers in the World Foundry Congresses held in China, Japan, and in many other Indian foundry congresses. Published technical papers in model aluminum pressure die casting in Google and Indian Foundry Journal and in many magazines. And received Best Paper Award in the year 2020 in Indian Congress held in Kolkata in September 2021, virtual platform. He had written book, namely Technology of Aluminum Die Casting through Case Studies. The book was fully sponsored by Institute of Indian Foundrymen, Kolkata. Positions held: Unit Head PDC in Sundaram Clayton, Padi, worked there for 35 years. General Manager, Dynamatic Technologies, Hyundai Ancillary, Sriperumbudur. And then retainer TQC in Sundaram Clayton for training for workmen to GET and engineers. Proprietor of Samurai Aluminium Foundry Consultancy. Technical consultant for foundries in Gujarat, Delhi, Bangalore, Hyderabad, and Coimbatore. Expertise domain, training of engineers and workmen. 7 QC, 5 years training as applicable to foundry with Tamil slides also. Core area, new die proving and problem solving in the shop floor. Guiding die design in PDC and GDC. It is indeed our pleasure to have Thirugnanam sir with us. Over to you, sir. You can start your presentation.
At the outset, I thank Main Minister of Untitled Chapter for giving me this opportunity to share some of my success stories of yield increments and cycle time reduction. I will present some live case studies. Aluminum castings are being produced by various processes. Some of them are sand castings and static gravity die casting, high pressure die casting, low pressure die casting, squeeze casting, and tilting gravity die casting. And there are nearly about 31 processes are there, and many more processes are there which are proprietary in nature. Those details are not much available to us. Foundry in general is an unique process. We have to pour more metal than the finished casting. It is really a handicap, but for the many other advantages. Molten metal yield can be defined as weight of the fettled casting by weight of the full shot yield 100%. This is a measuring way. And in sand casting, you can get a maximum yield of ranging from 30 to 40% only, and GDC from 45 to 55%, and tilting gravity can go sometimes up to 65. Normally it is around 55, 60, and high pressure also is the same range, 60, 65 only, and low pressure is quite good, it's 90, 95 also possible, and squeeze casting is also about more than 1992, and floating piston casting process, which is a proprietary process by Hyundai, they achieved even 95. I have seen my own eyes. And the semi-solid process also, you can get about 90, 98% yield, but that is not popular in India. There is one other casting developed by General Motors USA, that is riserless low pressure die casting, where you get 100% yield. There is no riser at all. So such an advancements are going on. And in India, the most popular process is GDC and HPDC and tilting gravity only. And sometimes there is low pressure also. So I will take some case studies to illustrate. What are the guidelines for improving the molten metal yield? Attempt to avoid bottom gating. As far as possible, do not go for bottom gating and side gating, since the racers become too cold and more volume of racers are needed for maintaining the same amount of feeding. Always try to use top gating, in which racers are always hot and volume of racers can be little less. Always attempt to use tilting gravity process, in which the riser and runners are one and the same. You don't have to have a separate riser and runner, both are same. Attempt to provide cord holes wherever possible in the casting to reduce the section thickness. Feeders could be avoided. Try to use high insulating die coating on the riser cavity to keep the racers hot with the reduced volume. These are all some of the guidelines which will help us to reduce the amount of metal poured. Let us try to apply the guidelines and try to make yield improvements. Case studies, will be giving 3 case studies I am going to take up. One is cylinder casting, and end cover casting, and the lever housing casting. 3. Of course, there are many more are there. Cylinder, this is the casting background. This is one casting. The short weight was 7.2 kgs, and the fettled weight was about 3.2 kgs, and percentage yield was only 44.4%. Aluminum alloy specified is LM4, and the silicon content, as you know, 4 to 6%. This is a hypoerotic alloys. Pressure tightness is a mandatory 10 bar, it has got to withstand. No salt blasting is likely specified. No ESD requirements. This is an under chassis casting. Here die was made, and we tried to make the casting, and this is the casting came out of the die. See, so much of races. This is a down sprue, which is coming down nearly about 120 mm, and then the metal enters in this one and go to the top, and it tries to fill the one. See, by the time the metal goes another 120, another 100, it's about 100, 220 mm material will be very, very cold here. See, it has not graying, is not seen at all. It is so solid like a biscuit. It is not at all feeding. from this one. This is one bulb racer. Now, a big static GDC was made to produce these castings were produced. And the casting quality was excellent. The die was running very well. And the yield was only 44.4%, which is very low. This one. This is the full shot. There are 5 races that runners were to be cut. See, this one, you have to cut here, then you have to cut here, and cut here, and all that one, and this one, and we have to relish and then make it even. Such a lot of fettling work is also there. It was decided to make improvements in the yield of the casting, also reduce the fettling work. We are thinking a lot. Let us see how the yield was improved in stages with the help of the guidelines. I will cite examples as you go by. First, we try to apply one rule, which is reduce the metal weight, or try to core hole can be provided wherever required. See, this is a heavy bars of 32 mm diameter, which was again tapped to M20 for being tapped on this. Supposing if you want to remove this racer, which weighs about 600 grams, we can attempt to core this and see. We did that. See, we have provided a core hole of 18 mm diameter through this, say 32 mm OD. This is the die. This is the one. This is the core. We try to put it from this one by modifying the die. This is the core. This is this one. Each in dia to a length of about 40 mm is quite a good material removal. And we try to pour some castings. A batch quantity was produced, and then the casting were okay. No shrinkage was there in this hole. So after machining, there was no blowhole in the thread. Thus, the side racer was eliminated by reducing the metal content, and the saving was about 600 grams. This is the first stage of improvement. The second stage is to remove the runner. This is a big chunk of material. Metal comes over there, get it depressurized, and then go into this area. This is the ingot, wherein try to fill the castings up. Also, after coming to this level, the metal goes up and then slowly it goes there. So it's a very long journey. This was a very bold and ambitious attempt, moving from the side gating to the top pouring. This was attempted in the second new die only, because we cannot modify the first die which is running. So we made a die and tried to block this out, remove this one and try to go for a gating like this, but still keeping these side races. This is the metal comes here and then it falls over there and falls over there. By this, very hot metal was there in this one, and the feeding was much better. But there were every flow lines were there. Here and here, flow lines are mixing up over there. But for the flow lines, no other defect was seen. However, a batch quantity of about 200 numbers were produced and machined, found no problem at all. But the flow lines were severe, but being an understages casting, it was accepted by quality department. The metal reduction was about 1.25 kg. How much metal was saved? There about 600, another 1.8 kgs of casting had been saved in the second attempt. This was a successful attempt. Then we also went here. Another one, why not we remove this feeder also and try to go for a bottom getting? This is really a very, very bold attempt. And we made one more die and see how it works. So here we went for a getting a ratio of 1:4:2. In the sense, the cross-sectional area at this place, say if it is 100 mm square, this will be 400 mm square, and this will be 200 mm square, so that no air will go into that one. So metal was flowing through this and falling on that one on top races, and these races have been connected so that the metal will go here. So there is no other way, there is no other races. Only one simple cut, we can remove the races. But lot of problems we encountered. There are 3 problems we saw in this attempt. very severe flow lengths, it was accepted by quality on our request. The movement of the big bottom core was getting jammed because when the metal falls to a height of about 150 mm, this 120, another 30, 150 mm, it gains a very velocity is very high. The velocity can be calculated is equal to root of 2gh. It works out to more than 1.5 meters or nearly 1.8 meters per second. By this one, this is the shank, this is the bore, this is the bore, and the metal straight away go into that one and make that die not movable at all. Then another problem we encountered was shrinkage in this area. So unless we solve these two problems, the project will be held up. So first we wanted to solve this metal entry problem. How to do that one? This I also had. No, stall blasting is not required. That is, we are able to get away with the flow lines. Though the flow lines were severe, and after stall blasting, these flow lines will sometimes will show up some surface defects. But we are lucky. No stall blasting was asked by the customer in this casting. So with the severe flow lines also, they're able to get away. Now, the gap is hardly about 0.3 mm per side. Unless we have 0.3 mm, the core will not go down. It's a very big core of 120 mm diameter, such a big core. A very long core of about, say, some 250 mm will be there, this height. And during production, when the metal comes at a very high speed on this one, see, this is the metal entry, then about 4 hours it gets jammed. Then we used to remove the core and remove this material and apply Mali coat also and then assemble. Dry will work for only 4 hours. Afterwards, again the metal will go inside and we have to remove and then remove it. So what we made is how to solve this problem on this one. This is a hollow core and this is the shank. Normally, the shank diameter is only 2 mm bigger than the core bottommost diameter of the casting. And this 0.3 mm is mandatory for free movement. If it is not there, the core will not drop because the core temperature will go up to 270 degrees by the time this expands and goes in that. And if it is 0.1, again the core jam. It's a very critical position how to sort it out. So instead of metal going straight away into this area, why not we make it that diverted by 90 degrees? So we made a core. Then we tried to make the clearance by only 0.1. 0.1 did not work. Again the core prime, but no metal entry. The problem is you can't operate it because after 2 to 3 hours, again, due to core expansion, the core jammed. So 0.1 clearance did not work in this area. Although the metal has not gone, that it has not worked well. So what we thought is, why not make the core shank bigger? Like this, something new idea, which is normally not done. This is unconventional way of making the die. We have made this core shank from the previous diameter to 30 mm more. So when the metal comes over here, it will not go here. It will get the pressure and it get diverted by about 90 degrees. By that one, the speed is reduced. Surprisingly, we found there is no metal entry at all. All over the place, it goes like that one. This is a very great idea. First time tried. But the diameter is very unconventional. Normally, instead of 2 mm, we made it 30 mm. There was no metal entry, there was no core jamming. But there was another problem. If the core shank is more, the casting goes down along with that one. So we have provided 4 resting pads on the die base like this. This is the casting bottom. This is the core shank, the cross-section area where the core moves down. We have provided 4 pads as a bearing area so that the casting is able to rest on this one and the core goes down. See, This is the core shank, which is about say 30 mm more. These portions are formed by the die base itself. So it is resting on this one and the core goes down. This was very much successful and we found the casting is working well. All the mechanical problems have been sorted out. There is one more, the last problem. The shrinkage on the center bars was still remaining. An attempt was made to solve the shrinkage problem by cooling methods. So this being a hollow core, we have admitted air inside. These are all air hollow core. These are all copper chills with a taper. This one, and try to solve the problem. Shrinkage was at the center bus was totally solved, but there was another problem, which is something different. Because when the air goes and then coming back, there was a compressor and a lot of noise was generating. And also some oil spillages in the compressor air. All the die space were getting so dirty on it. And there was a lot of objection from the shop floor. The whole shop was noisy. One compressor itself is exclusively required for this cooling. Lot of complaints from the workmen due to the places getting shabby all. However, it was tolerated by considering about nearly about 2 kilograms of material saving, yield improvement, eliminating band-sagging, etc. for some more time. But people cannot say tolerate for a very long time. 3 years passed without any more changes in the die. We made a fourth die. The shop floor engineers do not want to give it up. They want to eliminate the noise by avoiding air cooling. How? They formed a QC circle and with the senior die casters and start doing analysis. Why the metal is entering and how to sort out without these problems. This is a forum analysis. The man, machine, material, and process. All of you know very well. Heat conduction and hollow the core. Hollow core also is a reason because it contains air and air is a bad conductor of heat. Why not we make it solid? Then no air cooling was in the bottom core. Then we made a copper crystal. But this idea solved the problem of shrinkage. But again, it gave problem of noise and all that. Metal temperature was too high. Then we have brought it down to 720, something like that. But that makes no difference. Silicon is only 4 to 6%. There cannot be change. So boldly we want to make a solid core and try big bottom core. Then we made instead of steel, we made this cast iron solid core and replacing the existing hollow core, and trials were conducted. To our surprise, this hollow core, which was the existing core, we replaced the core by a solid one. See, big solid big core. Castings are produced and checked. To our surprise, no shrinkage at all in the center bus. And solid core was conducting heat very well. No problem at all. No air cooling was necessary. The noise was totally eliminated and the compressor was not getting overloaded. It was a very great success for us. This is before modification. So much of running a system and all that is there. After modification, from the weight has come down from 7.2 kgs to 5.5 kgs, and the yield has gone up from 44 to 50%. Just only one cut. We don't know how to cut this. This automatically breaks down. So we have to only cut this and later by only simple rotary sawing. It will solve. 7.2 to 5.5. The yield has gone from 44 to 62%. Let us work out the savings. The metal saving was 1.7 kg per casting and 10,000 numbers per month. And 12 months, 204 tons of metal you don't have to buy at all. At the time, the casting, the metal price was about 110 rupees per kilo or even 100 rupees per kilo. Savings by the way of saving meters of 25 grams by putting a code hole was about 3 tons of material has been removed whole years. Band sagging was totally eliminated and the top prices have been cut by a rotary sawing. It took us, may or may not believe, 7 long years and 4 new days were subsequently improving one after other. This was a very good experience for us. Another casting is a very small casting. This is an end cover casting, but it made a lot of problem to us. The weight is 120 grams, and the aluminum alloy is LM4, and the silicon is all same silicons, and pressure tightness is required. This is casting to be made. So we have made a two cavity die was made with two die halves and die base and the top core. This is the one. This is the die base with the cavity sunk in. These are formed by top cores, and these are the die half which is moving back and forth. This is the sectional view of this one. This is the running system, and goes. We follow only 142 sessions, and this is the riser on a big custom. These are all 2 car cores. These are all manually lifted core, each weighing about 5 kilos each core, and the casing has got to be removed. There is no ejection at all. The operator has got to lift the core every time, which is about 200 degrees centigrade, and then you have to lever the casting out and then take out the castings. Very strenuous one. Operators were afraid of operating this die. And this was the full shot of the casting removed from this die. From this die, we made a casting. This is the final shape of the casting that came out of the die. This is the casting. This is such a big riser with all that one. Short weight was 320 grams and filled with only 120 grams. Percentage yield is only 37%. Very, very low. On top of it, very difficult to hold this casting and sight. We had a lot of accidents also. One of the people cut his hands also. Very, very difficult to fettle the casting. So fettling also to be considered when you make a die. What are the problems in summary? The casting yield was only 37.5%. And the top core operation was very, very tiresome, and the casting removal by levering was also very hard and lots of time. Hourly output was only 15 numbers per hour. Unable to cut the big eraser by band sawing and sawing machines. We have made a lot of casting. You may not believe it. With a lot of heart pain, we have to remelt 2,000 numbers of these castings, which probably nobody else will do it. Then we want to make a new die. Then a new die was designed with the side pouring system. Something different. This is the die. One is a fixed die, wherein you make the cavity, and also this is a moving die. This one die half is a simple die stand, all that one. This is the gating system. This is the casting. The casting is like this. This is the top riser. This is the cavity, and also the side runner. The casting was coming out very well. The full shot of the casting. Short weight was 220 grams, and fettled weight was 120 grams, and yield has gone up very well from 30 to 35% to 51%. Sawing also quite easy. You can just cut it off on this one. This was not without problems. We had some problems in this area. Some shrinkage was come because this boss is isolated. Because this is a different one in these bosses. What we did, we put some, this is the core, we put some long copper chills with the air goes. Both the ends. This is a long one. And this copper chill and the air vent solve the problem very well. This is not a much a problem because this is nearer to the top risers. And this was a great success for us. Yield has improved from 37.5% to 51. That is, and output has gone up from 15 to 24 numbers per hour. 24 into 2 casting. See, 48 casting per hour, we are able to get it. Band sawing was very, very easy. This was the one success story. This is another casting, lever housing. This is also a very good casting. This is the shape. These houses and levers. This one, and the total weight of the casting is 0.72 kgs, and alloy is also again LM4. It's the casting. This is a rib, and this is color portions. A die was made earlier. This is a die construction, 2 die halves, and this is a big top core to make this board. To make this one, this profile, color profile, we have to make a top core. And this is a very heavy core. and it was pulled by lever and then take it out. And this bottom core for forming that 50 dia bore, these die house will move this way and that way. And this is the casting that came out of this die. This is found by the bottom core, this is top core. The entire thing is top core. See how many, these are run through the rib. 1, 2, 3, again 3 on that side is 6 plus 1, 7 racers are to be fettled. The full shot weight was only 2 kg and the fettle weight is 0.72 kg and the yield is as low as 34.2. And we require 2 operators also to operate this die. So management is not very happy. We have to make improvements. So there was one bold approach was made. Why not we make a die upside down like this? This is the die. This is the casting. These two are joined as a one bottom core. This one die. I didn't make the right drawing. And this is the top racer again as ever. We go for top pouring with a 1:4:2 ratio and try to fill the casting. And for the rib portion, we have provided a bulb racer to hold these ones. And to hold the casting on the base, we have provided this one because the core profile was totally different. It's a triangle come with this thing. And these two pairs were served as a resting point for the casting when the core drops down. And we found this die was working very well. And the old design, it was, this is the fettled weight that remains same for both the old and new design. The short weight is here 2.1. This is, you see, 1 kg, hardly 1 kg. This is 10. Tapping array is there is 1 kg. And the yield here, say 34.3% is 68.5. We got nearly double. And it requires 2 operators and here only 1 operator. And the output also has gone from 15 to 21 numbers per hour. It's a great success. Such a top gating, as I said, and so on. The end of this presentation, and say thanks a lot. Any questions? I am trying to answer. Yes.
Sir, good afternoon, sir. I am Neelan from SNAM Alloy, sir.
Yes, sir.
Sir, actually, I have one query.
Please.
In the production of aluminum metal matrix composite, through stir casting process, what are the ways or methods available to get good wettability of particulate to get the even distribution in the aluminum matrix, sir?
Actually, I should say very honestly, I am not knowing not having any knowledge on this metal matrix composite. I don't know at all. So
okay, sir.
I am not competent enough to answer that question. Sorry.
Okay.
Metal matrix is a new technology.
Yes, sir. Okay. Thank you so much, sir.
Sir, this is Babu from Asian Metals, Bangalore.
Yes, sir.
Yes, sir. Do you have any case study for tilting GDC like this?
Please repeat the question, sir.
Yes, sir. Do you have any case study for tilting GDC?
Yes, yes, I have. But today I could not present it. In fact,
because what happened is we are using most of the parts in tilting GDC.
Yeah.
So that will be very much helpful to.
In fact, I have planned it, but due to some time constraints, I could not make the slides. But tilting GDC is my favorite. All the time.
Okay, sir. So
John,
if
you can talk to me. I can share my slides afterwards. No problem.
I will do one thing, sir. I will can I get your mail ID so I can able to contact you directly?
Yes, it is there. It's nothing but say call bmthiru@gmail.com. Simple. CALLVMTHIRU.
Okay, sir. Yeah. Thank you, sir.
No problem. I will share my knowledge. Whatever.
Yeah. Okay, sir. Thank you, sir.
Sir, Thirugnanam sir, there's a question from Mr. Umesh. Explain about copper conical pins.
Yeah, I get the point.
Yes, sir.
Actually, when the top face absorbs heat, it is tapered down so that the heat is passed through this one, and these conical portions are very hot. And unless that is cooled down, these copper chips won't be effective. So that's why we are cooling the taper portion of the Copper. And this copper is 5 times faster than steel. Faster. And there are so many designs are there in copper chins. Even some chins are made straight and with the head 2 times the D of the diameter of this one. The head must be, and the main thing is that copper chin should be exposed to atmosphere. Unless it is not exposed to atmosphere, it will never get cold. The fin will not conduct. So I always make the shank and the head also, and the head diameter will be 2 times bigger than the diameter, and the thickness will be half the diameter. If it is done, it will generate a very good amount of heat can be removed. It will work.
Sir, there is a few more questions.
Yes, sir.
Every yield improvement die modification costs how much? Is a question from Mr. Gnanasegaran.
Please, beg your pardon, please.
Yield improvement die modification costs how much? He's asking, sir.
No, actually, the first one, we have to make 4 days successively. It took about 7 years to modify to come to this one because it's very, very costly dies. Even at that day, it cost about 4 lakhs to make the first day. Then imagine, because we cannot stop the day and do the modifications. So then we have to think, say, go by, make one by changes. Almost when we make that last day, it was about 7 years. 4th day was only. There will be a cost in currencies, but we save a lot.
Okay. Sir, what is the maximum part height recommended for top pouring in riser?
Beg your pardon, sir?
Maximum part height recommended for top pouring in riser.
Yeah, actually, the top pouring will be successful up to 150 mm height of castings. You can make a very good castings. Nothing more. Of that only you'll have problem. But
Okay.
the top pouring you must be careful because the speed of metal will be high. It will go into the bore. Up to 150, we have done it correctly. Nothing was not. Any casting can be poured.
Okay. Okay. Sir, next one question from Mr. Alagar Sami. Can you please give some suggestions to avoid flow marks in longer metal flow castings?
Beg your pardon, I'm a bit slow.
Yeah. Can you give some suggestions to avoid flow marks in longer metal flow casting?
Actually, flow marks is not difficult at all. It's only a question of the magnesium and other things getting oxidized while pouring. If they say the turbulence is reduced, the flow lines will be there. But when the turbulence should be avoided totally, the metal entry speed at the gate should not exceed 0.55 meter per second. But this 0.55 meter per second is not practicable. You will get a lot of cold sweats and non-fillings. We can go up to 1 meter per second at the ingate area without any much turbulence. Should that way you can avoid it. Only question of filling should be very slow. At the same time, if the wall is too small, it may lead to problems. Up to 1 meter, no problem.
Right, sir.
Then we answer the question.
Sir, next one is top pouring may create flow line casting due to air entrapment. How to avoid?
No, actually, this top pouring flow line is not a defect. The problem comes only when the customer is going to ask for short blasting, because all the air blow holes is only just below the subsurface defects. Only it will be 0.5, 1 mm down that is. As long as you don't short blast it, it will not be seen at all. If somebody is wanting to do some short blasting, all the surface oxides will come out and it will expose all the blowouts. That is the only thing. Actually, it is not these holes are not interconnected at all. So no leakage will come. It's only an appearance. So you must be very
one
careful
question
when
is,
customer is asking for shard blasting.
sir, next question is, can you recommend any simulation software?
Beg your pardon, sir, slowly.
Can you recommend any simulation software, sir? Simulation software.
The last sentence was not clear.
No, they are asking for any simulation software, sir.
Software.
Recommend any. Yeah, simulation software. Correct.
Yes, yes. It is very, very. You can put magma. Magma is very, very useful. It will tell you where the airlock is and where the sinkages will come. And the result will be, say, if you see about 10 mm wide this thing in the magma, in the actual case, it will be only half of that only will be there. Magma you can try, no problem. Only thing is you must be careful about the dye and the metal temperature inputs.
Sir, what is considered to be a good casting yield percentage in HPDC?
Actually, HPDC was giving a better yield. It was even 60 to 70% were there earlier. But nowadays it has come down because they have put a lot of chill vents. Here and there, lot of lines are passing. So it has come down even 5 to 10% has come down. Normally in those big dies with a lot of chill vents here and there, it comes even down to 53% I've seen. And also the machine capacity required is more when the area of the part line goes up. Because you are having lot of lines with all these chill vents here and there. It makes the die opening force more. So you got to go for a bigger size die because it's machine due to this one. It's also a loss. Normally, earlier one without chill vents and all, even you can go up to 70-78%.
Sir, look at this question. Is there any design without insulation for razors? Presently, we are using insulation. They are asking.
We are using installation.
Actually, sir, in our existing design, we are using for risers for compensating the shrinkages during solidification. We are using risers. In that risers, we are using insulation material to keep the metal flow and temperature to avoid temperature reduction.
Hello? Am I audible?
Yes, sir. Yes, sir.
Actually, what is the purpose of this coating the reservoir insulation? It is to retain the heat in the riser volume so that it can feed metal wherever it is required. So there is no design is there without coating these riser cavities. You have to coat it with insulating material. It's no other choice. As far as I know, it is still there. It is required. Otherwise, you have to go for a very big risers. Which you don't certify at all for a long time.
Actually, we are using insulated material by pasting, not by coating or like that. It is by paste. Pasting the material at around 8 mm thickness.
Any insulation coating for risers to get more hot?
Yeah, there are many coatings are there now. Actually, in the conventional one, you can use Fosico brands are there. Apart from it, in Korea, they got high ceramic insulation material that is in the form of paste. You can buy that paste and then paste it on the riser blocks. Sometimes it is not good to coat too heavy coatings or these kind of things, except for the bowl of the tilting rack. We want the riser to solidify immediately after the casting is solidified. If the riser is hot too long time, you cannot remove the casting. The cycle time is based only on the how quickly the riser solidifies. So it is not advantageous to keep the riser very long time. So you have to optimize the cooling rate just to feed the casting. But in the case of tilting gravity, you pour metal on the open bowl, and that bowl is very large and the volume is open. You have to keep the metal hot for a long time. And in Korea, I have seen in the bowl of the tilting gravity one, they coat a thickness of even half an inch thickness of ceramic die coat, and then leave it for 4 hours, 5 hours. Then put, and that coating will last for a month, for a year. I mean, for a month, but not for the gravity casting. Do not allow the riser to remain hot too long. It's also bad.
Right, sir. Sir, you can then answer the next question, sir. Any special chill coating available to improve cooling on mass areas?
No chill coating. Actually, coating is not chill at all. Actually, this coating is nothing but a parting of agent. It is not allowing the aluminium to come in contact with the iron. Iron and aluminium are very friendly. Even if you leave aluminium in a bare steel or cast iron, it will dissolve. Aluminium will dissolve iron material. That is why we are coating some kind of a die coat 34, die coat 140, and die coat on black die coat and all. So there is no chill coating.
Are there any further questions, sir, or we can close it?
You can use machine inserts this question.
Any further questions, gentlemen?
Yeah, there's one question here. I have to answer.
Yeah.
This one question from one. You can use machines inserts in riser section. These are customized and shapes available in the market. No, they should not be done. Actually, you have to make your design by yourself suitable to the casting. You can't buy this figure in the market and use it. That may lead to some problems also. Then another question: how chemical combustion impacts the flow marks through which elements organization can? Yeah, it's a good question. Actually, some aluminum contains even 0.4 magnesium. Normally, LM4, LM, and all they contain magnesium little. 0.4 not much. Some alloys will contain more magnesium, and magnesium is the only alloying element which evaporates and so on. So by controlling the composition of magnesium, you can control the flow marks to some extent. And these flow lines will become darker after 4 or 5 weeks at all. But without magnesium, you will find very difficult to achieve hardness in heat treatment also. So magnesium up to 0.4% is okay. Not much of problems. If the magnesium goes after that, no, 0.6, 8, and all, you'll have more problems. Have we answered your question? I don't know. Yeah, any chill coating available for sun core application. Yes, there are some proprietary chemicals are there. You can buy it and then use it for sand cores. It will cool down. Of course, but sand itself is a better conductor of heat, so there's no point in coating over it. Only finish can be improved.
Okay, I think we can. Any further questions, or we can close the season? I can go with vote of thanks. Okay, so gentlemen, we have had a very interesting webinar today on the topic yield improvement in aluminum castings. We are sure the contents of the presentation had a lot of takeaways for our audience. We'd like to thank Mr.M.Thirugnanam, a very senior aluminum casting consultant, for taking time off his busy schedule and sharing his knowledge with us and making us rich with knowledge. So we'd like to thank all our members who joined us on time and made this program a grand success. We from Chennai chapter will be conducting many more programs online as well as offline. So we'll be sharing information of the same with you, requesting you all to be a part of the same. Thank you very much. Thank you, sir. Thank you, Thirugnanam, sir, for a fantastic presentation. Thank you very much.
Thank you for the opportunity.
Thank you, sir. Thank you, sir.